Okay, well, this week we are finishing our read through the Sparse Virtual Shadow Maps article. And is the author here today? Because their Discord name is different than their Zoom name, so I don't.
Yeah,
Yeah,
I'm
Jay
here.
Stefano. Yeah, hello.
Hey,
Glad to have you back. Um, we
thanks.
got
Yeah,
through.
nice to be here.
Yeah, we got through the steps, the main 6 steps. And now we're going to go into some of the more details this week. So, um, modifying virtual viewport matrices. So we want to reduce the size of the viewport that is being rendered to try to get rid of false positives, so there's less need for viewport bound changes. May not be necessary with good object culling, but you know, this could be useful for other things. So we have each clip map's view projection matrix, and we modify it to only encompass the screen bounds in step 4. We want to render the part that changed and skip what didn't much more effectively. To do this, the matrix can be split into tiles and fractionally translated so that we can set the viewport size to be exactly the step 4 bound. I'm going to go and open this. So yeah, you want the viewport to be just the green box. Is my take from what that means. If we have a 64 by 64 page table, we have that size of screen tiles. Our normalized device coordinates go from -1 to 1 on x and y axes. 2 units wide, high, and deep. Oh, I guess with OpenGL that would be correct. I'm thinking in DirectX and Vulkan, and I think Meadowland. It's 0 to 1 on the z-axis, but I'm not sure how much that changes the way you do things, because you can still divide things up. It's just your z-axis is going to be 1/64th, not 1/32, 1/32. Let me also pop out the Discord chat. There we go. Okay. In case people post there. Okay. Min and max screen tiles. We get the range, and it's a vec2. And we merge it into the larger screen tile groups. We want to convert it. So this is the number of tiles. Oh, okay, the new screen tile size. Okay. Uh, okay, so it's just augmenting the viewport matrix by the bounds that we calculate. I mean, yeah, this is the new min screen tiles XY. And then there's a helpful link about tiling deferred rendering stuff, so there's help there. Translate and scale. Yeah, we don't need to do any rotate, which is very helpful. Very, very thankful. I'm very thankful for. Okay. How do we map virtual memory to physical memory? Let's look at the page table structure. Each entry in the table manages the state for 128 by 128 texels. The virtual resolution is set to 8K. The page table will need to be 64 by 64 elements in size. Oh, yeah, okay, so if we have a 8K virtual resolution and each page is 128 by 128, we need 64 by 64 pages.
Sounds right to me.
Okay. So we have our bit packing. We have a frame marker, which is useful for, I mean, it's only 4 bits, but I think you're never going to need more than, you're not going to have more than like 3 frames being rendered at a time if you have, but I guess if you might have up to 15 if you have a lot of deferred things, but I don't know what the frame marker, is used for. Let's read what it says. Okay, that are in use. 0 is unmarked, marked this frame, and anything greater than 1's meaning is marked a few frames ago but not currently needed for this frame. Okay. Yeah, so it could have been a single binary bit, used or unused, but by having 4 bits, we allow frames that were used in a previous frame are currently unused, but maybe they get reused in the future. I imagining that kind of thing, but not sure how you'd figure that out.
Yeah, it's like, well, like a picture your camera is staring in one location, and then it rotates a little bit to the left, and then within 15 frames it rotates back to where it was. Then the system would go, oh, I already have these in the cache, just reuse. So it would be, even though it panned, it wouldn't actually end up doing it. And that's if you add us.
Okay. Well, it's pretty useful.
So I have a question on that. So why don't you do like a least recently used kind of ejection or something?
Yeah, you could do that. It's I guess the frame marker is more to, like, if it's set, then it's indicating to the system that that particular page hasn't actually been freed, so you could have least recently used this. Basically, whenever the frame marker gets set to 0, you could switch over to the least recently used.
So moving on to the rest of the bits, I don't know if that answered your question fully, but we have a physical page index X and Y with, 8 bits per page. The lower left corner of the physical page in memory. So we have physical page index X and Y times 128. Okay, and we have, texels per page. So we have memory pool index. Okay, we have so it's for handling the possibility of there being multiple underlying textures that back the page. And because you might have a sparse image or just shared texture memory, you might need multiple images or multiple sparse images to store all the data. And then residency, whether it's backed or not, and then a valid / dirty flag. Yeah. Okay. Interesting that there's 2 bits per the residency status and the valid dirty status, but if you're not needing the bits elsewhere, then that's just fine. So we need a way of converting from world coordinates to virtual page coordinates and then to physical textual coordinates. 2 groups of matrices: projection view sample and projection view render. each frame of the projection view render matrix. So that's like the player camera, or just the camera matrix. Not camera, but the one that the regular geometry being rasterized is using. Whereas the projection view sample matrix. I'm trying to determine why this says very rarely change when view implies like the camera. Is that referring to like the position of the lights?
It's you mean for the projection view sample?
Yeah. It's saying
Yeah.
very rarely change, so that's kind of what I'm trying to grok.
Yeah, so it's basically for because like you were saying, the projection view render is for the rasterizer. So it's like we, as the player camera moves, we'll kind of shift it around so that we can capture the region around the player camera for each clip map. But then we run into this problem where it's like each one of those matrices only goes to 0 and 1, but we want a stable address space that doesn't change even when the matrix shifts. Otherwise, how are we going to reuse stuff from previous frames? Because it'd be like, how do we even reconstruct that address?
I
Uh,
see.
yeah, so basically the projection view sample just kind of sits stationary, and so for everything right nearby it, it's going to be from 0 to 1, but then as it goes outside, it's going to start going outside of that 0 1 range. And the way that we'll deal with it is we'll just end up doing coordinate wrapping. So like as it goes too far, it wraps back around and wraps back around. And this gives us stable virtual addresses, even as the player moves.
Oh, okay. That is very important then. Okay. So to go from virtual to physical, we do the following. Translate local clip map UV coordinates, the rasterization stuff, to virtual clip map UV coordinates. We wrap around any values outside the 0 to 1 range. We used wrap coordinates to access the page table and pull out physical XY offset and memory pool index. We used the physical XY offset and memory pool index to construct physical UV coordinates. And then, either read or write from those things. And so these will correspond to, this step 4 is actually having UV values and texture I was about to say sampler, and it's like, well, the Vulkan terminology is a descriptor, a texture descriptor. But, and then, do your work. So, okay. The stable virtual addressing is in the projection view sample matrix. Want it positioned around 0, 0, 0. And we have, an orthographic projection matrix, which is, I think it's standard for lighting to use orthographic projections in their, rendering of the shadow map. Okay, we have D sub k, the maximum view space extent of the first clip map, and Z is the maximum depth. Each clip map after the first maintains the same maximum depth, but doubles the extent. So, because we're dividing, we have 2 divided by, starting with 1, then 2, then 3, 4. Does it... do we double the value of dk, or... Okay.
Yeah, DK is doubled.
Okay, yeah. Okay. Yeah. So the global clip map origin view projection matrix is created by multiplying the orthographic projection above with a rotation only or directional light view matrix. Okay, so we just kind of grab the rotation part of the lights matrix light's position. I guess it's really, we're just looking at what the direction of the light is facing. Because we don't really care where in the world it is, we just need to know which direction it is. I guess. Okay. So the projection view render matrix now. All the local clip origin is the same as orthographic matrix, which is this guy, with the difference is that we add translation component to the local direction light view matrix. We want to change the clip origin so that we can render shadows in concentric rings around the player. You know, where we want the most detail. The upper third matrix is identical to the one used for projection view sample.
I have a question. So like, this is kind of assuming your world is like oriented on a plane, right? What if its world is more 3D? Like, and the player can move up and down. Does that change stuff?
It does, yeah. To an extent, it's and that was in the first part where I said that it doesn't. This projection view sample usually doesn't change, but the only time it might change is if the camera basically goes up and down
Okay.
to a point where it's like it exceeds the maximum depth. Then you might have to do like a condition for that, where it's like, okay, if the player goes above or below a certain point, we need to shift the projection view sample down so that we can capture the depth properly. And that's probably the main time where it'll shift. But otherwise, yeah, the directional light can just move with the player, as long as they're, they haven't moved up or down too much.
Okay.
Okay. I did not notice that the TX and TY, there was no TZ here, so it's a good observation. We do some matrix math, and then we multiply and get by a vector of the world position, and we get an even bigger matrix. That's a single vector, right? That's not a matrix. Yeah, okay. Okay, NDC coordinates for the first clip map. Oh. That's convenient if we need to convert back to if we just use the projection view sample, we can just subtract off these parameters. Okay. And then we don't need to do this derivation for each clip map. We can just multiply the result by 1 over 2c, where the c is the clip map index, minus 1. Oh, no, that's just the range, not... It's just 2 to the c, it's not 2 to the c minus 1. Yeah. We only need to pass one matrix, and we just convert as needed. And then we just take... Okay, yeah. Conversion functions for handling all of the clip map to and from world pose Okay, render clip map, sample clip map, convert clip 0 to clip n. Okay. Okay. We have everything we need to get to the physical coordinates. Given a world space coordinate, we'll calculate sample clip value and convert that virtual texture coordinates. You gotta get the page table entry. We use bitmask ops to get the individual XY offset out of the virtual texture coordinates. So I see an image load here for the page table. Is that just, this is just basically dereferencing, not dereferencing a pointer, but looking up the entry index from a data storage here. Yeah.
Yeah, you could store your page table as like an integer texture, and then find it as an image, and then
Yeah.
use image. You could also use a shader, like a storage buffer, if that was easier.
For a second, I was like, oh my god, we're having to do multiple image lookups. And then I realized whenever a CPU has its virtual memory, looked up, it has its own table of entries that it has to search through and, cache and do all that. So it's just making it's just re-implementing that same thing. So it's nothing new, or nothing really that different. Just a bit more convoluted because it's two-dimensional rather than one-dimensional. We unpack the data. We know that the pages are 128 by 128 in size. So we just multiply and calculate the virtual pixel coordinate and modulo it by 128. Oh. Oh, this is for each individual pixel. Right?
Yeah, that's right.
Okay.
Yeah, that's for like the. Because we have the page offset, but then it's like, okay, well, what pixel is it? So then we can imagine it.
In my head, I was thinking this was just trying to calculate the base of each page. But that's something you have to do already, so, Okay. Yeah, here is what I was thinking of. We take our offset, we multiply by 128, and we add the page texel offsets, and the third parameter is the memory pool index. Is that just for the system that handles the different memory pages that are textures or sparse textures existing?
Yeah, you could do like if you're using like a texture array, you could use it as that, or if you were doing some kind of bindless approach, then you could do like an array lookup or something.
Okay, that makes sense. And we're done! Whew, that is a lot of work. I mean...
Oh, and then the image up above is kind of showing like a visual of going from the page table. We use the XY offset, and it gets us to the bottom left corner, and then we use the physical page texel to get to the pixel.
Yeah. Wild. Yeah, in our step 6, this is the steps that we just followed. All that math and offsets and modulos. I mean, you look at all the logic that was needed to do this conversion, and you think, oh my gosh, that's a lot of work. I mean, you're doing some matrix multiplies, you do some, actually, yeah, well, it's matrix vector multiplies. The matrices are constructed once and shared. And it's just a lot of math, but to think about, well, every texture sample you do is going to be quite costly, and you got to use the texture space efficiently. The cost of doing all this math is probably not as much as it is just to allocate and sample a higher resolution, shadow map. So I'm just contextualizing how this virtualized texture system can really benefit performance, even though it's absolutely doing a lot of work to get from every possible virtual sample to a physical one.
Yeah, and then I know with something like Nanite, Unreal Engine's virtual geometry system, uh, for a lot of their virtual geometry, they can guarantee that each little meshlet, like individual submesh, will only fall within one page of the shadow. So they actually only do all these mapping steps once, and then they just reuse it for all the data within that page. So it's actually, for virtual geometry, it's even more efficient than
Wow.
having to do this multiple times.
I think I need to go and reread the Nanite presentation after we finish this, because I'll have a renewed appreciation for some of the things that are being described. Not appreciation, renewed understanding. Okay. We got to select our clip maps. There's the last week we went through the overview of the article, and this week we're answering a lot of the questions that were raised, or putting details to the overview that was given before. So, how do we select a clip map?
I have a question. So, is there any hardware that actually supports clip maps directly, or?
I think there was. I think I read it once in a paper. It was something like
Yeah, I
Silicon
read that.
Graphics Interactive
Yeah.
had a machine that could natively deal with them, but I don't think any hardware since
Okay.
then has ever done it. So everybody
Yeah.
since then has just been emulating it in software.
Right. Yeah, I read that paper a couple days ago, and yeah, the paper went along with actually having the hardware that did it. So yeah. But back in that day, you had to do it in hardware, otherwise it'd be too slow. So just a question. So like, since you're not using MIP maps, right? Or, I mean, do you have to do like trilinear filtering yourself, or like?
Yeah, there's some ways to handle it. This article will talk a little bit about that. I don't actually do trilinear, but the bi filtering, yeah, you kind of have like three options. You either do it all yourself, use a hybrid approach where you let the hardware um, do the filtering within the page, and then on the edges you do the manual part. And then the third one is if you can somehow add a texel border around every page,
Right.
then you can prevent it from going outside of the border, and then you can just let the hardware.
Right. Yep.
You said MIP maps in your question, and I'm thinking, for the purpose of shadow maps, there wouldn't be a MIP chain explicitly. I mean,
There actually could be. So with this one, the MIP chain is basically encoded as the clip maps, kind of surrounding,
right.
going outward. But if you go to something like a virtual point light or a virtual spotlight with a, because I know Unreal Engine does both of those, they actually do generate a virtual MIP chain for all 6 faces of the cube map or for the 2D textures of the.
Oh.
Yeah, so it could happen depending on the light type you go with.
Okay. Never mind then. So if we need to select the clip map and it's already between -1 and 1, where we're done, because it's just the first one. If we're outside of it, we need to multiply nx and y by 1 over 2 to the c. If we can solve for positive integer values of c, we get the clip map index. Okay, so here's that what was just stated, but in a formula where it's between 0 and 1.
Yeah, I'm kind of wondering if that's an error, but I don't remember.
Well, I mean, we're saying NDC on the range of -1 to 1. If it's outside of the range, we need to multiply
Yeah, it does look like an error, right? But yeah.
we can constrain the
kinda
positive
does.
values by taking the absolute value. So this would be, I think this one would be correct, because if you're taking the absolute value, there's no way you could get below 0. But
Oh, maybe that's what it was.
this one probably should be -1. I never liked inequalities in my algebra class in high school. I thought they were just confusing as all get out. So,
Yeah, I need to make a note of that to check that.
ooh, finding mistakes we are. Possible mistakes. Yeah, we don't really... It's the same logic for the x and y axis, so separating them out to just follow the logic. We can multiply everything by 2c to get rid of the divide. So we get 0 is less than absolute, and z less than 2c, 2 to the c. And we log base 2 of both sides, which just gives us c. So log base 2 of the absolute value of n on each axis is going to be less than c. We need to take a max because at n0 it's n log of... Yeah, we don't want to... It's undefined. Okay. And so if we just take the ceiling, we get the c value that it corresponds to. So we absolute value, then maximize it, the max between that and 1, so it just constrain that it's always above 1 or equal to. And then we log base to it and take the nearest integer rounding up, or the ceiling of it, not rounding up. That sounds weird. And here's the GLSL version of that. Okay. And okay, so because we computed them separately, the x and y, we have to combine them together, and we just take the max of both because maybe, it's not a pessimization, but it's just the larger of the two is the one that corresponds to the correct clip. We have a lovely view of the clip map changing. Is that some sort of compression? Like, can I pause? No, it's a GIF. I'm trying to... There's like a grid across the screen. Is that some sort of just like GIF compression?
Oh yeah, I see what you mean. Yeah, probably is actually.
Yeah, because I know GIFs have limited bit depth, and you got a lot of colors on here. But it's interesting because it's this kind of gradient, like pixel grid. It's not pixel, but
Yeah, I think I've seen that before in other GIFs.
Okay. I mean, what's great is if you take a GIF of the Hello Triangle, you can get some really rad color banding because it's a smooth transition, but, a smooth transition between red, blue, and green requires 16 million colors, supposedly. And, GIF is like, you got 256, we'll see what we can do, but it's not going to, be very faithful. But it looks rad because it's all banded to heckin' back and has a nice effect. But
They're probably doing dithering, right? In order to get around that fact that they only have
I
a
think so.
256 color palette. Yeah.
I'm referring to my own graphics adventures, and I'm like, can I find that image in any short amount of time? And I think the answer would be no, but yeah, it's not on my hard drive, or it's just not in my pictures folder, so I'd have to go search for it. Anyways, moving on, trying to work our way
Okay, so
through.
I have another question, I guess, on that section, right? So since you're not doing trilinear mapping, is there like, do you see like kind of discontinuous areas, like when you switch from one level of the clip map to the other?
Yeah, actually, you can. At least for mine, it's kind of like yeah, you can kind of tell the border, and especially like even with these visuals, you can kind of tell when the page size gets bigger, and then you're like, oh, that's definitely um,
Right.
a different one. I was seeing some images of Unreal, and it looks like theirs kind of isn't so clear. So I'm guessing what they're doing is, if they detect that it's on the border between one clip map and the next, probably just blend between them, kind of like how you would do with Cascade shadow map blending, and that should hide it a little.
Okay. Yep.
Okay. So, as some of you may know, the sun doesn't stay still and kind of moves. It's this weird thing that happens every day, all day. And we got to change stuff, because to do that in our uh, virtual shadow mapping, we got to modify some stuff, or at least just take into account.
I always love in some games you see the sun move and it's like choppy as it like snaps to a grid or something.
uh, Floating point errors at certain distances or some silliness like that.
It's actually funny with Unreal. If you read their documentation, they recommend doing exactly that with virtual shadow maps. Or like, instead of doing a continuous move, they recommend you do it in little chunks so that it has time to catch up.
Oh, yeah, okay. Because, yeah, if you're trying to re-render all of the shadow maps all at once, that's kind of a bummer. And if you're moving it, fractions of a second, I was gonna say radian, but then I realized, well, you got, degrees, minutes, and then seconds as like a division of the circle, because that's actually a pretty common way to do celestial object tracking, like arc seconds. I'm not making shit up, am I? Yeah, okay. It's not super useful because it's 1/60th, but you know, if you're trying to do a very small, yeah, okay, yeah. Wonder if there's another way to solve this moving light problem, but I guess there isn't one, and it's just doing more work every frame and not caching any of the shadow maps that you generated. So, yeah, if you have a lot of dynamic objects, you may need to do more stuff. And I think with Nanite and a lot of their render pipeline, I think they could very effectively figure out when things need to be re-rendered every frame, rather than just re-render everything and hope you can do it, hope it fits in the performance budget. Okay. moving on to allocation. And there's multiple ways to do it. One way, which is just maintaining a list of free pages in a SSBO. When we want to allocate, remove the topmost entry using atomics and assign to it. And then just add to the front of the list. I wonder, this statement implies it's a stack, when I'm thinking you could also possibly use a ring buffer, where you just a ring buffer. What is it? A fixed size wrapping ring buffer. So I guess that is just what a ring buffer is. But that way your freeze and your allocations are not contending on the same index. But I wonder if that doesn't really matter in practice.
Yeah, you could probably do that. And then there's the other way, which I don't think I mentioned it here, but someone brought it up earlier. You could actually use those frame marker bits and use that to implement the that least recently used and use them. Probably doing that by the default would be. I personally didn't do that, but I could see that being a really good way to do that.
Yeah. Okay. Well, that's just knowing when you have a free and non-free page, or allocating pages. You need to get those pages from somewhere. You could use hardware API, which has issues, and like we talked last week, you kind of have to go through the CPU right now, and it sucks to do that for a very GPU-driven architecture. You can kind of just do it yourself with just writing your own sparse memory functions and stuff. You just create a regular texture and texture arrays, and then handle all the textures yourself, and assigning and unassigning things. So this is a nice GIF just showing the light moving through the scene, but the bottom right here is the actual shadow map, and well, the black square here is the actual virtual shadow map space, and then down here the actually allocated and used pages. Are you just writing gray for every black pixel just to make it show up, or is that some artifact of the GIF?
Let's see. So the black. Oh, you mean like where they kind of are these little popping black ones?
Well, no, the popping black ones are just pages that aren't used from the looks of it. I'm trying to say is the gray just in actual texture memory it'd be black because it's a shadow, right? Or am I?
Oh yeah, it's just the depth value. It's
Oh, it's the depth
yeah,
value. Duh.
Yeah.
I'm stupid.
It's the depth value. And
yeah.
Then,
so that's why it's not pitch black, because it's
Yeah, and I think I linearized the depth here. Maybe that's also why it looks a little more.
I mean, it's a debug view. It doesn't doesn't correspond to reality or anything.
Yeah, and then the hardware one, you see like you see the little black, like see how they're kind of popping all over.
Yeah.
It's because with sparse APIs you can tell it like individual pages you want to deallocate, whereas with software sparse you're not going to be able to do that, so you'll have more consistent.
Okay. Yeah. I mean, it's fascinating to watch this as the shadow moves, because you can see the various pages that you would in the scene map onto the same visual segment, but here they're split up by table, so it's kind of like the same motion in multiple pages. It's kind of cool. How do you deal with running out of memory is up to you to decide how to deal with it. You could allocate more memory when you run out. I mean, at some point you might be limited by the available system resources. And of course you can also try to go and do some deallocation of unused pages. Another, I guess you could do both of these at the same time, but just if you have a fixed size thing, you try to just prioritize more important clip maps. Okay, and so here's a harder approach, but would have guarantee that each clip map has all available physical memory it needs. Okay. So
I have an observation or question about this. So like, the one thing they mentioned in the clip map paper is that, you know, you have your screen resolution, which is, you know, however many million pixels, and you know, in theory, you should only need that much memory to store all of the shadow information that you need. Because, you know, it would be optimal if there's one shadow pixel for each pixel on the screen. So maybe just because the way the algorithm works, there's some like maximum physical size that you would never go above just because of the way the algorithm works and the number of pixels on the screen.
Yeah, you're actually probably right. I personally didn't look into that, but that might be. And I also don't know what Unreal does for that. But yeah, if that was true, then you could just calculate like the worst case, which would probably be something like, you know, the sun is like right at the horizon,
Mm-hmm.
like really horrible situation, and figure out how much physical memory, and if that's doable, then yeah, just do that at startup and then never touch it again.
Yep. I guess the whole point of that observation is that maybe you don't need some complicated eviction, or not eviction, but, you know, complicated scheme if like it could never happen, right? Yeah.
Yeah, that's true. I guess for that one, it was just mostly like if you wanted a system where you could say like, oh, I want this really tiny texture budget, then it's like, you know, it can still deal with it. It's just you'll get situations where sometimes it
Right. Yeah.
totally fails.
So why don't you evict the more uh, fine pages? I mean, it's like if you evict all the coarse ones, then maybe you won't have enough memory for the fine ones. I don't know.
Yeah, you could. That would be an option. Yeah, you could say like one strategy could be like, okay, well, I ran out of memory. Let me start evicting fine ones because I know the coarse ones use less memory, and then I'll just fall back to like lower resolution data. And I guess you would see some of the shadows suffer, but yeah, that might be the better way.
Yeah. I guess the thing to do is to actually test it, like have a really small physical buffer and see what happens. Yeah.
So the hardware shadow filtering, I think you mentioned this earlier. You know, we can normally perform its filtering and we have no issues in the 126 by 126 interior, but every border pixel has a problem of being on the border, and, you know, your filtering kind of needs the data, or the data needs to not be from a different page or a different, you know, shadow map, so that things look consistent or continuous. Yeah. You could add a one texel border around each page. Then we just use hardware filtering and say, oh, the border color is blah. Is that a correct interpretation?
Yeah, that's right.
Okay. Hybrid. A sampling function that checks to see if we are starting texels on the boundary. Performs software shadow filtering. If not on board, use hardware filtering as normal. Manual is just don't use hardware shadow filtering. I mean, this would just be hardware texture filtering, right? And you just implement all that in your own code. Okay.
Yeah, I have some questions or observations on this stuff too. So,
Yeah.
so what's like? Do people know what's the cost of having? Oh, I guess it doesn't matter in this case. I was going to say, what's the cost of having a texture that's not actually a power of 2 size? But I guess here your pages can be not power of 2 because you're actually doing all the math yourself to figure out
Yeah, that's
where
true.
you are. Yeah.
If you don't use the the hardware sparse API, then yeah, you can map it however you want.
Mhm.
And I think that was, I don't know for sure, but I think that's what, like with ID's virtual texturing, I think that's what they did. Might be wrong. But if you go with the sparse API, the hardware actually imposes limits on, like it says we support these page sizes and nothing else.
Mhm.
The thought that came to mind was this entire system is predilected upon having essentially one camera. And everything is only visible through that one camera. Now, I'm not saying that you can't have picture-in-picture stuff, but that the algorithm as presented here is, assuming that you just have the one viewport. And you're not trying to render, like 4 separate viewports, like for split-screen co-op or something like that. However, I don't think that actually is a problem because you just have 4 small... You just do the same logic 4 times, and each one of those, 4 viewports would just have a much smaller budget because we're trying to match up the screen resolution to shadow resolution. So you wouldn't need nearly as many pages as you would for a full screen thing, because you're just dividing up your resources. You have more overhead possibly, and more bookkeeping, but that's not really a huge problem.
Yeah, I could definitely see a case where they could yeah, I think definitely, or the easiest way would probably be just to have, if you did, let's say, split screen, you could generate 2 dev buffers and then analyze each one separately. And then, for some of them, they might have a lot of cases where they mark the same pages, and then that would mean you just do it once, and then they both get to save the same data.
Ooh, yeah. I'm just
then,
imagining Mario Kart split screen.
Yeah, I guess one situation that could get difficult is if they're looking at like totally different parts of the scene. Then I guess the kind of going back to what we were talking about earlier, with the, like, what's the worst case memory budget? I don't know. Maybe you would have to like calculate worst case and double it, something like that.
Yeah.
Well, and it seems like you have a similar problem with point lights, right? Or multiple directional lights. You have to have a separate shadow map for each one, right?
Yeah, like I think with Unreal Engine, they all share the same physical memory pool, but yeah, with something like point lights and spotlights, my understanding is their current recommendation is for any case that you can place a spotlight with a directional light, and then for the point lights, they recommend only using as few as you can get away with, because they eat up a lot of memory.
So can you mix like use this technique for directional lights and then something else for point lights, right?
Oh yeah, that's true. You could do that.
So and like Unreal Engine does global illumination, right? Does that it all meshes together, I guess, somehow.
Yeah, there's. Let me think. I don't know how their lumen deals with. I don't know if it has to use any of the shadow data. I guess is what I'm saying.
I don't think it does, because it's kind of, it deals with color more than anything, and it's
I think they have like this irradiance cache, right? And then
yes, yes.
when they're rendering into the irradiance cache, they would have to do shadows correctly.
Indirect lighting cache. I don't see where they talk about so can I just do lumen? Okay.
I guess in that case, there's a lot of stuff off screen that could be doing lighting, and so you can't really use shadow maps this way. You have to do
Yeah.
kind of like more ray tracing kind of stuff.
Yeah, and I think that's what they do fall back on is like ray traced. What do they call it? Ray trace, because they use that like 2-level for.
Yeah, they have a they have like a global cache and then a local camera specific one.
Yeah, and I think for software, like if they're on a hardware that doesn't support ray tracing, they fall back to ray trace sign distance fields or ray trace height maps.
Yeah.
And then
yeah.
I think on hardware ray tracing, they just do. I think they do hardware ray tracing their irradiance cache. I might be
Okay.
wrong though.
Yeah. Oh, right, and they had like some limit the number of rays that they do per frame or something.
Yeah. I mean, you can make something look pretty, but you can't have too many pretty things on screen at once, no matter what render method you use. Just because if you want things to look pretty, it takes computation and or memory, and so... Okay, well, unless you have more questions or comments, I think we can end the recording here. We actually got through it in around an hour, which I'm a little impressed by.
So I would like to hear what. Jay, I don't know what your name is, but I'll just call you Jay. Like, what, stuff is left to do, or what? Like, you have any comments about like how it went?
Like success of it.
Yeah,
Or-
I mean, are you happy with what you ended up with, or?
Yeah, it's. I would say like comparing it to. Right now I'm running this on a GTX 1060, and the performance of a 4K shadow map with multiple like 4 to 8 cascades or clip maps is roughly the same performance as I was getting with my old unoptimized 1K shadow map cascaded with just 4. So it's like it definitely gave a huge increase in resolution and for about the same because it's able to cache so much.
Right. Yeah.
I think what's left is definitely how to effectively, and some of these I know Unreal is still working on, like how to effectively handle invalidations like with dynamic objects. I think they're trying to move towards that dual memory pool system where it's like they have static that doesn't change much and then they have dynamic that's changing all the time and then they just merge them together when they're doing the sampling. Let's see, other things are I know they're doing a lot of work on virtual point lights and virtual spotlights. Sort of like they're trying to find ways to enable per light resolution scaling, and I know they're also going heavily into per light like rendering budget, so you can say like, okay, this light I only want to update this many pages per frame so that if I have a bunch on screen I don't totally wreck my performance. And then I think long term, I could honestly see this being like the last great attempt for shadow maps. You know what Unreal is doing? Like they kind of went for this, where it's like, okay, let's just do a total virtual memory system to get as high resolution as we can, and I think they're going to go all out with this. And then I could see Unreal 6 just switching to ray tracing and just saying, okay, that was the last great shadow map attempt, and that's it. Let's go to ray tracing.
Yep. It does seem like a really, really good algorithm, to make shadow maps. I mean, if you have a large enough physical buffer that they're just like almost perfect, basically.
Yeah, and I think especially like for mine, the performance was decent, but I'm not using virtual geometry. And from my understanding, at least from when I was reading the Fortnite blog, it sounds like if you merge this with their virtual geometry, you get like an extremely good pairing where you can reuse tons of work. Cache invalidations tend to be very local, so like if an object moves, it tends to invalidate only like a very small number of pages around it. And actually, Unreal recommends that if you want to go all in with virtual shadow maps, that you virtualize as much of your geometry as possible. So
I do want to say that virtualize geometry in this context just means a nanite geometry, right?
yeah, I think it's like the nanite where they're trying to match the geometric resolution to the screen.
Right, because it's really like I say that only because the geometry is still geometry. It's not stored in an alternate format, but the way Nanite stores the various level of detail and patches, it makes it super fast, and you get the visibility buffer determining what actually needs to be rendered, and so yeah, you get great occlusion culling, very fine detail occlusion culling, which just feeds into the virtual shadow maps, where if you have really good occlusion culling, you can get away with so much.
That's my understanding too. Is that it's it's real geometry. It's just super high resolution, like film grade, and then they build their own level of detail hierarchy, and so you get. I think that's the other thing with Nanite is you get automatic level of detail that they can do smooth transitions between, and so you get.
So they do call it.
And it's when they're rendering the various levels of the clip map, they can use different LODs, right, of the geometry.
Oh yeah, that's true. Yeah, they can do that.
Yeah.
I guess I was just confused because they do call it virtualized geometry, but the term virtual geometry is kind of overloaded, so I think the goal is similar. Like they're trying to get a sort of 1-to-1 pixel resolution for not just the geometry but for the shadow maps. So it's like right.
They're trying to bound the amount of work that I don't know if that's the right term, but they're trying to match the resolution, what's actually needed in memory versus what's seen on screen. So I think that's why they go together.
Right. Yeah, I wish there was. Is there a visual picture showing? This is just the usage guide. Oh. This is the low detail. It's like a user's guide. Ah, here we go. Yeah, the different patches. All the different patches. I guess virtualized is correct here because they are trying to maintain a near 1-to-1 screen texel to mesh polygon or triangle density. Where you have a handful of triangles per pixel at most. Yeah, that's the view I was wanting. Where like each pixel corresponds to one triangle, or near enough one triangle. Okay, yeah, no, virtualized is a good term for it. I guess I'm just like so used to virtual being used in other contexts that I thought it was inappropriate for some stupid reason, even though it's very appropriate. Okay, well, I think I'm gonna end the recording here then. So thank you, Jay, for hanging out and answering all those questions. It's been really awesome.
Yeah, thanks. glad we got through the whole thing.
Yeah.
Yeah, thanks a lot for coming.
Well, thanks for writing it because this is
Yeah, thank you.
very interesting and useful.
Oh,
Yeah,
yes.
it was me and a couple other people we were really interested in what Unreal's been doing, and we just thought, hey, maybe we can cobble it together. And when we finally pull it off, I thought, well, I should probably write about it. So
Well, how long did it take you guys to do this?
we started it in August, and
Okay.
I would say it was mostly finished in September, and then through October it was just fixing a bunch of bugs, and there's still some bugs, but
Yep.
so,
I don't know.
yeah,
I have the urge to try to implement this too. So, but I don't know when I'll get around to it.
yeah, it's definitely really interesting. I learned a lot that I didn't know, and it's definitely doable. Especially if you just say like, okay, I'm only doing directional. You could even say, I know a lot of people started out with I'm not going to do any caching. Then all of a sudden it becomes really manageable.
Mhm.